Intelligent Transportation Systems Podcast. Hello, welcome back to the ITSPodcast. Thanks for being back. I'm Javier Sanchez Medina from the Intelligent Transportation Systems Society. We have a brand new episode ready for you, a selective production for your information and enjoyment, just for our unique community. In this episode, we have Professor Jeffrey Miller interviewing Professor Petros Ioannou at the University of Southern California campus. Professor Ioannou is such a reputed colleague in the field, for example, for his contributions to adaptive cruise control systems. Our partner, Professor Miller, did conduct a marvelous interview at Professor Iannou's office, so we have this amazing piece of information right from the front. We also have our usual news mini-section by Maryam Kaveshgar, a very illustrative transportation in history mini-section by Mehran Shirazi, and a very interesting book review by Professor Eren on a book titled Theoretic Analysis of Congestion, Safety and Security, Traffic and Transportation Theory. And that's it. We believe you will enjoy it. Let's start with the Transportation in History mini-section.
Transportation in History by Mehran Shirazi, PhD candidate at Simon Fraser University, Canada. A brief history of transportation before the 16th century. In previous episodes of Transportation in History, we have talked about the history of modern transportation in the 20th century in details. In this episode, we briefly review the timeline of transportation technology from the beginning up to the 16th century. Land transportation. The first form of transport was, of course, the human foot. However, people eventually learned to use animals for transportation. Donkeys and horses were probably domesticated between 4000 and 3000 BC. Camels were domesticated slightly later, between 3000 and 2000 BC. Meanwhile, about 3500 BC, the wheel was invented in what is now Iraq. Animal-drawn wheeled vehicles were probably developed in the ancient Near East in the 4th or 5th millennium BC, and spread to Europe and India in the 4th millennium BC, and China in about 1200 BC. Other early wheeled vehicles include the chariot. The first earth tracks were created by humans carrying goods. With the growth of trade, tracks were often flattened or widened to accommodate animal traffic. The Romans had a significant need for good roads to extend and maintain their empire, and developed Roman roads. The invention of horseshoes at 770 improved the transportation by horse significantly. Water transportation. In the Stone Ages, primitive boats developed to permit navigation of rivers for fishing in rivers and off the coast. It has been argued that boats suitable for a significant sea crossing were necessary for people to reach Australia an estimated 40,000 years ago. At about 3500 BC, riverboats were invented. They were simply dug-out canoes. People lit a fire on a big log, then put it out and dug out the burned wood. At about 3100 BC, the Egyptians invented the sailing boat. The sail could only be used when sailing in one direction. When traveling against the wind, the boat had to be rowed. Romans built stronger ships, which could carry 1,000 tons of cargo. Compass was invented in China at 11th century. By the 12th century, Europeans learned to use it too. Rudder was invented almost at the same time. It made the steering of ships much easier. By the end of 15th century, ships were made with 3 masts. Famous ocean-going sailing ships at the time were the Arabic Caravel in the 13th century, the Chinese treasure ship in the early 15th century, and the Mediterranean man-of-war in the late 15th century. Aviation. Humanity's desire to fly likely dates back to the first time man observed birds, an observation illustrated in the legendary stories of Daedalus and Icarus in Greek mythology and the Vimanas in Indian mythology. Much of the focus of early research was on imitating birds, but through trial and error, balloons, airships, gliders, and eventually powered aircraft and other types of flying machines were invented. Kites were the first form of man-made flying objects, and early records suggest that kites were around before 200 BC in China. At 1492, Leonardo da Vinci was the first person to seriously theorize about flying machines. He had over 100 drawings that illustrated his theories on flight. In the next episode, we will continue the history of transportation after the 16th century.
This is the book review section for the present issue of ITSPodcast. Reviewed by Dr. Haluk Eren, Fırat University, Elazığ, Turkey. The book title is Game Theoretic Analysis of Congestion, Safety and Security, Traffic and Transportation Theory, and consists of 220 pages. Edited by Kjell, Hausken and Zhuang. The book was produced by Springer in 2015. This book is dedicated to ITS researchers, whose chapters are prepared by different authors. It brings a new horizon to traffic management. As reading the book, researchers may find useful examples for this trend topic, connecting between congestion and game-based safety or security for traffic and transportation. The book recites sample congestion problems in ITS via game theory involving safety or security. This approach may lead researchers to get new horizons and to see the research trends in this field. Although the literature is full of congestion models, safety and security-oriented studies are limited. Furthermore, most game theoretic approaches do not include in congestion. The book establishes a well connection to relevant research fields and provides a strong mathematical foundation. It intends to handle congestion-related systems, streaming in parallel, series, interlinked, or interdependent on one way or both ways. For game theoretic analysis, minimum 2 players should be ready. Multiple players can be adversaries against system reliability. The players may have their own concerns about system safety or security. Governments, companies, and agencies may possess effective software to tackle with congestion and safety or security against various threats. Let's briefly look at the highlighted points of the existing studies. Study 1 consists of 41 pages, and it is written by Felipe Valencia, Jose Lopez, Alfredo Nunes, Cristian Portilla, Luis Cortes, Jairo Espinoza, and Bart de Schutter, entitled Congestion Management in Motorways and Urban Networks through a bargaining game-based coordination mechanism. Authors suggest game theory-based distributed model predictive control, DMPC, to test road traffic networks. Such large-scale systems need distributed control strategies. The control of the traffic network refers to a cooperative game, since the MPC local controllers are able to communicate with each other. Their payoffs are the local performance indices, such as avoiding congestion. Therefore, players may establish a well-balance between local and global performance. Distributed strategies consider that whole traffic network composed of different subnetworks, possessing local optimal controllers. In this approach, local control decisions of a single subnetwork are influenced by the decisions for other subnetworks and vice versa. Study 2 recites 26 pages, written by Chuanfei Dong, Yishi Chen, Shi Mang, and Bokai Chen, entitled Advanced Information Feedback Coupled with an Evolutionary Game in Intelligent Transportation Systems. In this chapter, authors focus on a mean velocity difference feedback strategy and a congestion coefficient difference feedback strategy for ITS. Both strategies have time-varying nature for feedback information. This approach provides better stability for route flow. The authors also discuss information feedback via evolutionary gain in a one-to-one lane ITS under dynamic periodic boundary conditions. They present an improved self-questioning Fermi updating mechanism using the self-play payoff. Existing scheme brings several advantages over the regular Fermi method. Study 3 consists of 24 pages, and it is written by Ioannou, entitled Solving a Dynamic User Optimal Route Guidance Problem, based on Joint Strategy Fictitious Play. The author introduces a multiplayer game in a dynamic multi-agent transportation system, considering user compliances to form system administrator recommendations. Users exploit their experience to estimate travel time via different routes. Informed or non-informed users deal with joint strategy fictitious play. They adapt their route choices progressively to reach their destinations. The dynamic user optimal route guidance problem is formulated as a variational inequality problem in a quick-form traffic flow model. This approach can solve the present problem via local outgoing user link choices. Study 4 consists of 22 pages, written by Theodore Tsekeris and Ivannis Katerolos, entitled A Psychosocial Agent-Based Model of Driver Behavior Dynamics. Authors introduce a psychosocial agent-based model for interaction between drivers. Heterogeneity and dynamic adjustment responses are involved in the system to simulate driver behavior dynamics under different types of interaction among vehicles. Cognitive processes, risk assessment, time responsiveness of driving behavior, control dimensions of neighboring drivers, and the topology of interaction give results in fixed point, periodicity, and transient chaos. Proposed model reveals the role of both cognitive processes and interactions of drivers on their actual driving behavior. Outcomes show that the established system improves the level of service, safety, and security in roads. Study 5 consists of 30 pages, and it is written by Kjell Hausken and Hubert Ribon. The title of the article is Game Theoretic Context and Interpretation of Kerner's Three-Phase Traffic Theory. It is chapter Common Games in Traffic Theory such as the Chicken Game, Battle of the Sexes, Prisoner's Dilemma, and Coordination Game are presented. The authors mention about Kerner's three-phase traffic theory game, applying to the Chicken Game. Density rise strengthens the chicken strategy because drivers in a congested street become anxious and fearful of accidents. The three phases are free flow and two congested phases that are synchronized flow and white moving jam. Number of chickens is changed via the hysteresis in a density versus flow rate diagram. Study 6 consists of 16 pages, and it is written by Mengyao Gao, Bo Zhang, Vicky Bier, and Tao Yao. The title of the article is A Heuristic Method for identifying near-optimal defending strategies for a road network subject to traffic congestion. In this study, authors investigate the vulnerability of road networks to interdictions. An attacker interdicts links to maximize congestion. In this case, network traffic flow follows user equilibrium traffic assignment. However, it is influenced by interdiction of attacker. In this problem, the role of the defender is to minimize damage caused by an attack. A heuristic method is proposed to solve this problem. The effectiveness of the approach is demonstrated by simulation results. As applying numerical experiments to different Cartesian grid-like networks. Study 7 consists of 32 pages and written by Antonik Ohazulaik, George Steele, Walter Kern, and Eric van Berkum. The title of the article is Multiple Stakeholders in Road Pricing, a Game-Theoretic Approach. Authors suggest a game-theoretic approach as an alternative to the multi-objective optimization models for road pricing. They establish a non-cooperative game, when each player pursues different road pricing strategy to control possible conditions in traffic, such as congestion, air pollution, noise, and safety. The game is sequential, and the leaders set link tolls in the first stage. Then, road users choose routes in the second stage. It is essentially a Stackelberg game, involving multiple leaders or actors in the upper level determining link tolls, and road users are followers in the lower level. Their route choice is adapted to the applied tolls. Authors come up with a first best taxation schedule to establish a scenario lacking niche equilibrium. Study 8 includes 20 pages by Katerina Stankova, Alexander Badovizhin, and Eric van Berkum, entitled Stackelberg and Inverse Stackelberg Road Pricing Games, State of the Art and Feature Research. Authors focus on game-oriented toll design to enhance performance of road traffic systems. In their opinion, road authority have primary role as leader in deciding the toll, and the drivers are given secondary role as followers reacting to the toll by adapting driving behavior and thus impacting traffic flows. Considering the toll structure, the authors formulate the problem in twofold. A Stackelberg game when toll is uniform or time varying, and an inverse Stackelberg game when toll is traffic flow dependent. This chapter discusses existing results and case studies of proposed framework. To say more about the book, it needs mid-level ITS congestion and game theory background. In addition to congestion preliminaries, it promotes feature research in this game-related domain. Existing chapters are supported by relevant theory, and many of the arguments are sketched by descriptive figures. Reader can find the references at the end of each chapter. As a final word, hope you enjoy as reading the book. Thank you.
This is the news mini-section for episode 33, March 2016 by Maryam Kaveshgar. January was a very exciting and eventful month for our industry. Starting with CES in Las Vegas, the driverless cars had a great show. All of the top automakers were at Las Vegas presenting their plans for future driverless cars. By far, automobile industry had the biggest leap in CES 2016, most probably following the footsteps of Google, Tesla, and Apple. One of the tech companies in automotive industry which captured the eyes of everyone is Faraday Future. Their concept car FF01 with a futuristic design was unveiled at CES. The most interesting fact in their design is the so-called variable platform architecture. The company has arrived at this point in just 18 months. Faraday Future has pledged to invest more than $1 billion in the plant, which will be based near Las Vegas. Apart from the very well-known companies in autonomous driving, Kjell from South Korea also promised to bring its fully driverless cars to the market by 2030. They are already testing their electric cars Kia Soul on the streets of Nevada. Renault-Nissan Alliance also claimed that over next 5 years they will introduce 10 semi-autonomous or fully autonomous vehicles. Maybe all these achievements and news was the reason that in January, President Obama announced a $4 billion fund for autonomous vehicle research. This budget is dedicated to fully autonomous vehicles and not semi-autonomous cars, mainly aimed at level 4, that is cars which have complete control with or without a driver on board. Nissan has made intelligent parking chairs which are inspired by its self-driving cars. They work with just clap of a hand. The layout of the room is pre-programmed with each chair assigned a spot at the table. And finally, Porsche CEO Oliver Blume has announced that his company is not after driverless technology. He believes that the one who owns a Porsche would like to drive it. With so much enthusiasm and frenzy going around the autonomous cars, subscribe to our podcast to get the updates.
Hello again! Let's go now with that interview performed by Professor Miller to Professor Petros Ioannou. We hope you like it.
Hello, today we are with one of the most prolific researchers in our field, Professor Petros Ioannou from the University of Southern California. My name is Jeff Miller, also a professor here at USC, and it's my honor to interview him today. It's very difficult to summarize what he has accomplished in a few minutes, but I'll do my best here. Professor Ioannou received the bachelor's degree with first-class honors from University College London, England in 1978, and the MS and PhD degrees from the University of Illinois, Urbana-Champaign in 1980 and 1982, respectively. During the period from 1975 to 1978, he held a Commonwealth Scholarship from the Association of Commonwealth Universities, London, England. He was awarded several prizes, including the Goldsmith Prize and the AP Head Prize from University College London. From 1979 to 1982, he was a research assistant at the Coordinated Science Laboratory at the University of Illinois. In 1982, Dr. Ioannou joined the Department of Electrical Engineering Systems at the University of Southern California in Los Angeles, California. He's currently a professor in the same department and the director of the Center of Advanced Transportation Technologies. His research interests are in the areas of control and applications, adaptive and nonlinear systems, vehicle dynamics and control, intelligent transportation systems, marine transportation, congestion control of computer networks, and neural networks. He was a visiting professor at the University of Newcastle, Australia in the fall of 1988, the Technical University of Crete in summer of 1992, and served as the Dean of the School of Pure and Applied Science at the University of Cyprus in 1995. In 1984, he was a recipient of the Outstanding Transaction Paper for his paper, An Asymptotic Error Analysis of Identifiers and Adaptive Observers in the Presence of Parasitics, which appeared in the IEEE Transactions on Automatic Control in August of 1982. Dr. Ioannou is also the recipient of a 1985 Presidential Young Investigator Award for his research in adaptive control. He has been an associate editor for the IEEE Transactions on Automatic Control, the International Journal of Control and Automatica. He is currently an associate editor of the IEEE Transactions on Intelligent Transportation Systems, which he has recently now become the editor-in-chief of, associate editor at large of the IEEE Transactions on Automatic Control, member of the Control Systems Society on IEEE ITS Council Committee, and vice chairman of the IFAC Technical Committee on Transportation Systems. Dr. Ioannou is a fellow of IEEE and the author or co-author of 5 books and over 150 research papers in the area of controls, neural networks, nonlinear dynamical systems, and intelligent transportation systems. On top of all this, Professor Ioannou has earned the IEEE Transportation Technologies Award for 2016, which says, quote, for contributions to the design, analysis, and implementation of adaptive cruise control systems, end quote. Professor, welcome to the ITS podcast.
Thank you for the invitation, and I appreciate the brief description of my CV, and I'll be glad to participate in this effort of passing out information to the audience of ITS.
Great. Well, congratulations on the IEEE Transportation Technologies Award. This is quite an honor, and I'm sure you are very proud of the recognition of your hard work and research. Can you tell us how you began your work in automatic cruise control?
I would say it's adaptive cruise control versus automatic. I got involved with the control in automotive back in 1978 when I spent summer internship with Ford Motor Company, and then later on as professor at the University of Southern California in the early 80s, I got funded by Ford and General Motors, and we did a lot of work on drive-by-wire, steer-by-wire, and a lot of automated features that became very important more recently. So my work on adaptive cruise control started in the late 80s when people were talking about platooning and full vehicle automation with very short distances between. And our approach, based on the experience we had with the automotive, was this is not feasible given the state of the technology, and most likely what would happen is a more of an evolutionary type of progress in the area of automation. And that's why we started thinking about automating one direction, mainly the longitudinal direction, where we can put some sensor in front of the vehicle, sense the environment, and based on that, adjust the brakes and the throttle to keep a safe distance from the vehicle in front. So we try to do the minimum possible so that the technology becomes implementable without disturbing the infrastructure and a lot of other things. For example, in the case of platooning or vehicle following, there was a need for vehicle-to-vehicle communication, which in our case, we show that we didn't need to have that. And you could achieve vehicle stability and string stability by just, instead of having a constant space headway, you have a constant time headway. So the bigger the velocity, the bigger the distance between the vehicles. And we came up with a couple of papers, and that attracted the attention of Ford. And we developed several designs for Ford. We went to the proving grounds, we tested them successfully, and we worked with Ford to get it down to the implementation stage by doing all the failure modes analysis and the software code that eventually got implemented on actual vehicles. And the only issue that remained at that stage was certain liability issues with the sensors. And we tested different radar sensors and a LiDAR. And we understood at the time the limitations and also the capabilities of these different sensors. And after that, I think Ford and later on other automobile companies continued the work, and much to my surprise, it became a commercial item much faster than I thought. I thought it would take some time to resolve all these liability issues associated. In case of an accident, whose fault is the manufacturer of the sensor or the designer of the adaptive cruise control?
Sure. So we have these issues arising in more recent times with a lot of the driverless technologies related to adaptive cruise control systems. What do you think the next big advancement is going to be?
Well, the initial adaptive cruise control systems, the driver was responsible for emergencies. In other words, you switch the system on, the system will brake, accelerate, decelerate after a certain speed, but it will never do an emergency stop. So the driver is expected to take over in case of emergency. Also, the system wouldn't engage below about 20 miles per hour. Later on, they extended that to at low speeds also. So the next development, I would say, is the full automation in the longitudinal direction. In other words, allowing the system to brake for you all the way to an emergency stop. And also the lateral, which becomes very important and is much more difficult. How do you keep the vehicle in the center of the lane? And without talking about lane changes, which is also a tough problem. But keeping the vehicle in the center of the lane, again, will depend on the accuracy on position sensors and again, how do you sense the environment. But this leads to a fully automated vehicle, which a lot of people are experimenting with right now, including Google and all the automobile companies.
Yeah. So a lot of your experience has been in automatic control of intelligent vehicles. And we see so many automatic driving demonstrations already from some of the companies that you just mentioned and other research universities and institutes that it seems like we're able to drive, stay in lanes, sense other vehicles. Are we not done yet? What still remains? What challenges still remain in this field?
Well, the challenge is emulating the human eyes and the human senses and decision making. In some sense, humans are inferior to automation because automation can act much faster, shorter reaction times. But a lot of times there are sceneries or situations where the automated system may not be able to handle, and this is something to be seen. So it's all about the emulating the human ability in a truly driving environment, and how so there are a lot of issues that will be coming up. I'm not sure, I don't believe that the automobile companies will develop a vehicle similar to Google, that it will be go by itself, driving around even without a passenger. I think they will expect the driver to serve the purpose of a pilot. So the driver will be monitoring what's going on, probably will go through some training, and then he or she will be responsible for the driving, for if something goes wrong. That's my feeling.
So there have been some theories recently that if you mix human control and automatic control, that it may actually be more dangerous because of a re-immersion period that humans have when, if they're not paying attention, they're distracted and then they need to take over control of the vehicle.
Well, that's one of the big problems. When you are in the fully automated mode, your reaction times go up. So what do you do? That's one issue. The other issue is what's going to happen to traffic. For example, the way we drive today, we drive dangerously, but for a few seconds. Mm-hmm. So you cut in front of a vehicle, but you expect the vehicle behind you because you look at the driver, you know that he saw you, and you know he's going to brake, or you rely on his ability to brake, and we do that all the time. So in these 3 or 4 seconds, we are in a dangerous situation, And sometimes you do have rear-end collisions as a result. In most of the time, things work out. Now, an automated vehicle cannot put itself in such dangerous situations by design. No manufacturer will do that. Will allow the automated vehicle to cut in front of another vehicle within a very short, especially manually driven vehicle.
Yeah.
If it's an automated, if the other vehicle is automated, maybe they communicate, maybe they decide something, but
right.
The automated vehicle, it will not communicate with a human-driven vehicle,
Sure.
right, to negotiate these things. Whereas the human driver will communicate. When you look and sometimes you put your indicator, you look at the driver next to you, and the driver may wave to you, go.
Sure.
And so when you mix the two up, you don't have this interaction anymore.
Mm.
And what would happen if a manual vehicle hits an automated vehicle? What would happen in that case? Who's going to take the automated vehicle out of the way? So there are a lot of issues that people, I think that people are thinking about them. I mean, the automotive, I'm sure they're thinking about it. Now the question, why are they all rushing? Because I think it's all about connectivity. The next generation of people want, they're the Facebook people, they're the iPhone people. They want to be connected, and these things sell, even if people don't use them. So there is a competition there. The question, who is going to take the first step, like Google, let's say, look, I'm going to put a vehicle out, and I'm going to put not just 20, 50, but million of them to be roaming around, and I will take the liability cost. We have to see whether that will happen. Because we know from probability that if the probability of an automated vehicle getting into an accident is, let's say, 10 to the minus 9, very small.
Yeah.
Now, when you produce 10 million vehicles, the probability of at least one of them getting into an accident, it becomes close to 1.
Right.
So these things are we have to see how it is, what's going to happen. What we know, what is surprising and really interesting is that everybody's rushing in that direction. So we have to see.
So there's been some manufacturers like Audi who says by 2019 they expect to release their first fully autonomous vehicle, where you just type in an address of where you want to go and you sit back and the vehicle is going to take you. Do you think that 4 years from now is rushing?
I mean, it all depends on the performance of these sensor technologies, which there has been a lot of development in sensor technology that I'm not familiar with. I mean, I don't know, because the way the automotive does it, they do failure modes analysis. They look at every single piece of equipment and they perform what is called failure modes and effects analysis and see. So how, whether they did that and what kind of probabilities they came up with and whether these probabilities are satisfactory is something to be seen. The other thing which is confusing, autonomous vehicles. So the driver can see, doesn't have to do anything, but do they mean whether the driver is there or not, it doesn't matter, or they expect the driver to take over? Mm-hmm. There will be some warning that the driver now take over because I'm making a mess or I cannot figure out the environment. So we have, this definition doesn't come out. They say autonomous vehicle, but they don't clarify.
Yeah.
Is it pilotless?
Yeah.
Or with a pilot?
Right.
Because the Airbus, for example, the pilot doesn't have to do anything. A lot of commercial airlines, the pilot does very little.
Yeah.
But he's required to be there.
Right.
And the technology for a fully automated commercial aircraft has been around for more than 30 years. Yes, we don't have any commercial aircraft that is fully automated. Why? Right. That should concern us, right? Why don't we have it? The technology is there, it's safe, but yet no one will fly some of these planes without a pilot. Nobody's risking it.
Is this kind of on user acceptance as well? I don't know how comfortable I would feel getting into an aircraft without somebody in the
Exactly.
cockpit.
Exactly. And the same thing maybe with the vehicles. How comfortable would you feel being in a vehicle with no driving wheel, just buttons? And what if you mess with the buttons? What kind of authority does the human will have in an automated vehicle? Zero authority? Some authority? I mean, I asked 10 people, what is the function of a neutral in a vehicle? And 6 of them didn't know, and they're all engineers. So we assume that because we do research in the area, we understand things. But if these vehicles are given to all kind of humans who have no idea about engineering and how these things work, how are they going to perceive them? And what are the kind of tasks they are expected to play? So at one point, if the vehicle is fully automated, you just open the door, you sit in, and it takes off. And then, can you open the door after that? Can you open the window?
Yeah.
What can you do? What are the functions the driver can do?
Yeah.
And is it possible that they do something that they endanger themselves or endanger other people? So these things are not, I haven't seen them discussed very much, including the ethical part,
Right.
where you have to make a decision whom to kill.
Right.
So it's interesting. On the other hand, whether these things materialize or not, I think a lot of useful technology is coming out that is going to be helpful in a lot of other areas. So everything is positive. I don't see any negativity in that. But
Yeah. So the automotive industry has really become a big player in the consumer space. Like the Consumer's Electronics Show in Las Vegas each year is dominated by
Right.
the automotive industry now. You were part of a large multi-university project called the Audi Urban Intelligent Assist. Can you tell us about this work and how it fits into the consumer landscape?
with the Audi Intelligent Urban Driver Assist was a project funded by Audi, and the whole idea was to put things on the vehicle that makes it much more easier to drive in an urban environment. And some of the issues that we addressed was intelligent navigation, intelligent parking assist, and we came up with the idea of personalization. Because when you give instructions to drivers, every driver has different characteristics, driving characteristics, and also different habits. So we developed some algorithms for predicting of traffic, predicted travel time, and things like that, that were also based on what kind of driver you are, whether you're an aggressive driver. So there was a lot of learning in the background, trying to figure you out. And we came up with very good ideas, actually, and we developed the system that has been implemented on Audi for parking and also for navigation and personalization. You could distinguish two people, even though they're the same age, the same education, and so you can tell who is who within 15 minutes of gathering data. So with the intelligent parking assist, we did prediction. For example, you're going from here to Santa Monica, will I find parking? What are the parking possibilities do I have? And what is the parking that fits my needs better? Mm-hmm. Whether it's I like to park, pay less and walk, or whether I like valet, or whether I like a structure, things like that. So everything was a combination of machine learning with some prediction and stochastic modeling. The good thing about the project is that we eventually implemented it on the vehicle. And we tested it in Los Angeles and San Francisco. Great. So it's usually the case when you do something so successfully, you expect the project to renew, but what is most of the time is happening, they hire your students.
So it's good for the people working on the project.
Yes.
But not the PI on the project.
Right. So the people got a job.
So some of your work has also been in adaptive control for air transportation, which isn't a big area of research in our conferences and journals. And as you had mentioned recently, we've been having like autopilot for 30 years or more.
Right.
What additional work do you see that needs to be done as far as air transportation is concerned?
Well, we need to understand that the way the aircraft is controlled has been an example for drive-by-wire in the vehicles. Has also been given as an example to get rid of a lot of steel on the vehicle, make it lighter, use computers and wirings, sensors, to achieve a much better efficiency. So now when you press your gas pedal, you are not opening the throttle. You are sending a command into the electronic module, and the electronic module decides about the throttle and the spark advance and the air-fuel ratio and all these things. So we get much more efficiency now with a computer-controlled vehicle. But these ideas were borrowed from aircraft control, which is it was more advanced. My involvement with aircraft control had to do with autopilots on high-performance aircraft and failure modes and effects analysis. And we had a few projects with the Air Force on that, and some companies in the area, and we still do, where we design controllers for various cases. For example, if the plane is damaged, can you use redundant surfaces to still control the aircraft? And if you can't do that, what do you do? Can you go to a lower performance? And so on. And that becomes very important in the case of UAVs, because the pilot sometimes can take action and manage the aircraft. But if it's a UAV, you may decide whether you want to destroy it, whether you want to land it somewhere, whether you have any redundancies in software or hardware to be able to bring it back. So there are a lot of problems there, but I would say the aircraft problem is a little bit easier in some sense than the vehicle. Because you don't have you have a trained pilot, and whereas in the vehicle, in a much more clear environment, more degrees of freedom for safety.
Yeah.
Whereas in the vehicle, you are concerned of all kind of obstacles that are coming towards you.
Hello again. I want to make an initial use of this middle cat to pay tribute to these podcast volunteers. They are working month after month, stealing time from their jobs, families, and personal situations to share it in a very professional way with this publications community. Kudos to all of them. In particular, I would like to say a big thank you to Dr. Maryam Kaveshgar for her news mini-section, to Mehran Shirazi for his Transportation in History Cats, and also to Professor Haluk Eren for his book reviews. It is amazing having them on board and to learn from their commitment and generosity. Thank you. Now let's get back to our today's interview.
You currently serve as the Associate Director of Research for METRANS.
Yes.
Which is a transportation center that is between the University of Southern California and Cal State Long Beach, if I'm correct. Can you tell us more about this center and what type of research is happening there?
The center is one of the university centers that are across the United States. I think they have 20, 30 of them, I don't remember. And the center has funded for 2 years with much funds from different places. And our center is focusing on metropolitan issues, and specifically on freight and ports, because Los Angeles has two of the biggest ports in the United States. There's a lot of freight movements. There's rail and congestion network, road network. So there are a lot of problems and a lot of technologies that need to be developed to make the system more efficient.
And it seems that a number of the projects that are coming out of METRANS dealing with the port have to do with trucks traveling. And you had a report recently, the design and evaluation of impact of traffic light priority for trucks on traffic flow.
Right.
Can you tell us a little about that?
Yeah, that was a project where we noticed that sometimes when a truck is approaching a traffic light, it might be better off for all vehicles involved, not just the truck, to let the truck go to extend a little bit the green light so it goes out of the way. The reason is that every time the truck, if you load the truck, stops and accelerates again when the traffic light goes green, it causes several problems. One of the problems is that it causes a delay because it has a slower movement. Mm-hmm. It produces much more pollution. It consumes more fuel. And more important, it causes more damage to the road. Mm. So there are a lot of advantages for all traffic involved to let trucks go in some cases. Mm-hmm. So what we develop, we look at the network and different algorithms of when do you make a decision to let the truck go and when not. So you don't want to let the trucks go and then create a big queue on the other way, the other side. Sure. So trying to do something that it doesn't pass, it doesn't increase delays for other passenger cars to the point that it will not be acceptable, and yet it benefits everyone. It benefits the environment and the efficiency of the system. It's a little bit different than the bus priority, where the bus priority, you always give priority to the bus no matter what. Mm-hmm. But in that case, the bus is, they're not as frequent as the trucks. Sure. So like if you go in the Port of LA Long Beach area, 20-30% are trucks. Right. So you have to take that into account. Right.
Another publication of yours that was published by the IEEE Transactions on Intelligent Transportation Systems was titled Driver Vehicle Response Diagnostic System for the Vehicle Following Case. Can you explain a little bit about that paper for us?
Yeah, that's a case of what we call personalization. So we know that every driver drives differently, but also every driver-vehicle combination is a different response. Mm-hmm. So if you drive a Mercedes, you're going to drive differently than you drive a Toyota, a high-power one. Mm-hmm. If you drive a sports car and a truck, you're going to have a different response, right? So you look at these combined dynamics. So you look at the vehicle following response, and we say, okay, how can I model the driver? So in 15 minutes data, we develop a stochastic model for the driver, and then we predict its acceleration, and we compare it with its actual acceleration. And the two usually match pretty well. Now, if you get another guy to test the model of the previous guy, you see a big difference. Oh. And that's what we demonstrated with the Audi vehicle on this personalization. So we use a Gaussian mixture model approach, some prediction techniques, to demonstrate that we can really, the vehicle can have this in the background without disturbing the driver, right, and learn what kind of driver you have. Right. And then once you have that, you know that, every time you go to the vehicle, you press a button, and they have this feature right now. So your seat gets adjusted, your mirrors get adjusted, right? And now the vehicle knows that it's you who is in the vehicle. Yeah. And then, knowing how you are expected to respond to the environment, it can tell whether you are drunk or if it's going to give you navigation suggestions, your estimated travel time. It can take that into account. It can use it for parking assist. It can use it for all kind of warnings, and so on. And this is really significant because if you develop, let's say, a warning for all the drivers, you're going to have the situation that some drivers may find it too conservative and they're not going to like it. And some drivers may find it too dangerous and they're going to ignore it. So the acceptance will go down. But if you customize these warnings based on the abilities of the driver, it has a much higher chance for acceptance. And that's what motivated this personalization that we are still researching about. Wow. We think that's a way to go.
Wow, that's interesting.
Eventually, because now with computers and capabilities to run a lot of computations and big data, we can do that. Technology is not an obstacle. Yeah. So I can write software.
So do you think that this could be useful with driverless vehicles
Absolutely.
As a training model, where maybe it's not the manufacturer that programs the vehicle in a certain way, but the driver gets to, in a sense, program it just based on maybe they drive it for a couple weeks before the driverless portion takes over?
That's what I think. We did another paper on that, how the automated vehicle tune itself to to the perceptions and responses of the driver. So it appears more naturally to the driver when you go around the curve, when you change the lanes, when you do vehicle following. Someone asked me at the conference, why do you want to do that? Because a lot of people are excited about automated vehicles because now they're going to have a very good driver.
Yeah.
They have a choice of a good driver. And I said, what's a good driver? What's a good driver for you, the young person? It may be a different good driver from an older person. For me, a good driver is a person who drives safely.
Yeah.
For you, as a good driver, is a person who does maneuvers.
That's possible, yeah.
And it's exciting. So the whole idea is to have options so the driver chooses.
So if that's the case, though, are we taking away some of the safety that we could embed in driverless vehicles, though? If we allow the vehicle to learn bad habits of a driver, is that decreasing the safety of it?
We are not talking about learning bad habits. We are talking about doing things that they are compatible with the perceptions and reaction times of the driver. So it doesn't become too slow or over-aggressive. So you never copy a bad habit.
It would still be a safer vehicle than a human-driven vehicle.
The safety by definition has to be included. Nobody is going to build something that compromises on safety. It just they're not going to be risky liability issues. So the safety has to be satisfied. It's the bottom line. It's a red line, as they call it. From there on, within the safety regime, you can make adjustments that fit different driving styles.
So you talk about a range of safety. Ideally, we would want every vehicle to be at the top of that range, though. So is there some range that maybe is acceptable, that one vehicle has a smaller probability of getting into an accident than another, but both are still considered safe?
No, let's assume that the automated vehicle, have a headway of 0.3 seconds, right? And it's absolutely safe. Okay? But 0.3 seconds may not be acceptable for many drivers. So there are drivers say, look, I don't feel comfortable, I cannot even see the bumper of the vehicle in front. So I want 0.5, 0.6 seconds.
Okay.
I'm talking about that thing. The minimum, the 0.3, cannot be violated.
I see.
The system will not allow a driver who is aggressive and say, I want to go down to almost bumper to bumper.
And so as far as the technology is concerned, the safety would be the same, but the perception of the driver and passengers would be different.
Exactly.
Ah, that's interesting. So, recently you were elected as the editor-in-chief of the IEEE Transactions on Intelligent Transportation Systems, which is the first publication from the IEEE Intelligent Transportation Systems Society. And in January, you take over that role. Can you tell us what your plans are for this publication?
Well, the plan is to continue the progress that has been made in this new society, capitalize on, continue to improve quality, attract more people, the attention of more people to the journal, have a very meritocratic and transparent process of reviewing and paper acceptance, and the usual hard work that goes with every chief editor. It's a big task. I take it very seriously. My objectives is to improve quality and engage as many people as possible. There are a lot of well-known people in transportation that they haven't been publishing in our journal, and it's a good idea to reach out to these people through special sessions or invitations to get their attention to the journal, which I think our journal is emerging to be the top journal in the area. And the reason is that the IEEE stamp, because this is all about transportation, it's going to be all about technologies. When you say technologies, you mean electrical engineering, communications, computers, electronics, and so on. Transportation area is rather primitive right now. If you look around, you have very limited sensors. We don't know what's going on in arterial streets. Like in Los Angeles, only 20% of links are instrumented on the arterial network, and this is going to change with vehicle communications and all these technologies that are inevitably coming in.
Yeah. Great. Well, I want to thank you for your time today, Professor Ioannou. This has been a great interview. Hopefully our listeners are going to agree with that. You have any last words or advice for anyone?
Well, thank you very much for interviewing me. I don't have advice for anyone. Just drive safely. Continue to work hard and do good research. Yes, some researchers will be following this. But thank you very much for giving me the opportunity to say a few things regarding the area, where things are going. And all I have to say is this is a very exciting area. I think more things will be coming. The new technologies and will signal a lot of new research in the area of transportation, which is good for us, for our PhD students. And I look forward to working with everyone in the society in that direction to make society much better.
All right, great. Well, thank you.
And that was it. We truly hope you enjoyed this issue and to receive your feedback. Remember that we are just launching a YouTube channel for these episodes, so you can also follow us there if you want to. This podcast is sponsored by the IEEE Intelligent Transportation Systems Society, website designed and managed by the Innovation Center for the Information Society at the University of Las Palmas de Gran Canaria in Spain, soundtrack developed by Rubicon, audio edition, post-production and dissemination by the Institute of Cybernetics at the University of Las Palmas de Gran Canaria. I'm Javier Sánchez Medina from the IEEE ITS Society. We'll be back soon bringing you again the cutting edge of science at the Intelligent Transportation Systems podcast. Thanks for listening and drive safe.